Okay guys, today's in this video we are going to discuss one more important component of power electronics which we call DIAC. DIAC, as the name signifies, diode plus AC. It is a diode which is used with the AC voltage. Since it is used with the AC voltage, it means it will obviously be working in both the directions. That is why DIAC is a two-terminal bidirectional avalanche diode, because it works on the principle of avalanche breakdown. So we call it an avalanche diode, which can be turned on in either direction of the input voltage. Means if the polarity of the input voltage is changing, it will continuously be working the way it was working in opposite polarity. So it is a bidirectional device. So in general we can call it this is similar to a track. Track was also a device which was working in both the direction. So it is also called as a track without gate terminal. Since it is a diode, so it should not have a three terminals. That is why it's a track with two terminals, or the absence of gate terminal is there. So it's a diode which is working with the AC voltage. So, and the basic purpose of diode, this DIAC, is to trigger the track. So there is a brother sister relations between this DIAC and track. Sometimes it is seen that the track cannot be used without a DIAC, and DIAC has no independent use in power electronics. So let us see how it is made and how it is working. So as far as construction concerned, as I had already told, that it is a track without gate terminals. So there is a construction exactly similar to the track we already had studied in our previous videos. There is P and P, and this is N is there, and one more N is heavily doped, and there. So it has two terminals, MT1 and MT2, as it was in track, but there is no gate terminal. So obviously the symbol is also similar to the track, having no gate terminal. So this is, and moreover MT1 and MT2, there is no anode and cathode. Since it is a bidirectional device, so there is a symmetry in its construction as well, and terminals are not marked as anode and cathodes. So let us see, this is the basic construction. This construction is simplified in two different ways over here to understand its bidirectional working. So we will explain this when we will go through the workings. So we already have told it is a two-terminal device. It is a track without a gate terminals, and the construction, as far as construction is concerned, all the layer of these devices are identical in size and identical in doping as well, unlike to other devices. And both terminals are interchangeable because there is a symmetry in the construction, so both terminals can be interchanged. So as far as working is concerned, how does it work? So we have made this construction in simplified fashion here also. So MT2 and MT1 is over here. Let us see, MT2 is positive and MT1 is negative. So let us see how does it work. Now if MT2 is positive, then what will happen? P2, and this is in forward junction, and since it is in negative terminal, so N to P, this junction is also in forward junction, forward biasing. However, J1 junction will be in reverse biasing. So if the voltage is applied in this polarity, the device will not conduct because one junction is in reverse bias. If we will increase the voltage, then still no current will flow through the device because of its reverse biasing, one junction in reverse biasing, but a small leakage current will be there. If we exceed the voltage to a certain limit, that times the J1 junction will experience the avalanche breakdowns. Once it is in breakdown region, so this junction was in forward bias, this junction was in forward bias, and this junction has got in breakdown. So the device will conduct heavily. So at certain voltage, we call that voltage at breakover voltage. At a certain value of the voltage with this polarity, this junction will break down and the device will conduct. Heavy current will flow through the device and device will conduct. We call that voltage breakover voltage. Once the device has started to conduct, heavy current will flow through this and the voltage across will becomes very less. this small voltage, after turning on, the small voltage across it is called breakback voltage. So this is the way this device will turn on in this direction. Now if the polarity is changed, since it is used with AC voltage, the polarity will obviously get changed. So if in opposite polarity, what will happen? MT2 negative and MT1 as positive. That times the device will work in this way. So this is positive terminal, this junction will forward bias. This is a negative terminal, this junction will negative terminal. So this junction will reverse bias, this forward bias, this junction will get back in reverse bias. So this way one junction is in reverse bias, so device will not conduct with this polarity. Now if we will increase the voltage, we will continuously increase the voltage, there will be a small leakage current in this direction. But at a certain voltage, again this junction will experience the avalanche breakdown and device will conduct. So that voltage at which the device turns on is called breakdown or breakover voltage, and after that and heavy current flow through the device in this direction also, as shown in the green arrow. So what we have seen so far is that whether the polarity is in this way or in the reverse polarity, there is a certain voltage at which the device will start conducting symmetrically. In either direction, it will be breaking down or it will be turned on at the same voltage. We call that breakover voltage. So we can conclude the working of the diode that this is being turned on symmetrically in either direction. That the voltage lies around 30 to 50 volts that the device gets turned on. So let us come back to the VI characteristics, which will make it very clear that how exactly the device is reacting or behaving with the application of voltage in either polarity. So suppose we have applied the voltage, this is a VF, we are applied the voltage, the device being one junction in the reverse bias, the device will not conduct, only small leakage current will be there. This leakage current is quite different from that what we already seen in the conventional diodes. So this leakage current is there at this voltage, we call that breakover voltage. Once the device that at this voltage, the device will get turned on. As soon as the device is turned on, that junction gets breakdown, then the current will increase very heavily through the diode, and voltage or through the DIAC, and the voltage across it will decrease, and this voltage will stop up to the breakback voltage. So this is the gray colored portion is the turned on region of DIAC in this polarity. However, this yellowish region is where the diode DIAC is in off state. Now if we reverse the polarity, that times the same things happen over here. There will be a small leakage current through the device, and at this voltage, breakover voltage, the device turns on, the voltage across it reduces up to breakback voltage and current increases. So this is the negative resistance region in the turning or turn on region of the device. So what we see through this VI characteristic that it is of working symmetrically in either directions. So this is a symmetrical device as well. So in this graph also we can see that if we apply this AC voltage directly across the DIAC, so initially the DIAC will not work because one junction is reverse bias. At this voltage, we call this, suppose the breakover voltage were equal to this voltage, the DIAC will get turned on. Once the DIAC is turned on, the power will be supplied in the outputs and it will zero up to here. Again in opposite polarity, these things happens and this DIAC will turn on at this voltage and power will deliver to the output. So what we see that it is a triggering pulse is being generated depending upon the timing of the turning on timing of this device, and the turning on depend upon the breakover voltage. If we reduce the breakover voltage, it will get turned on easily early. So this is the way the output power is controlled. So here also we can see that this is the input power, input AC power applied to the DIAC, and DIAC is making is the power reduced levels because it is being turned on at this peak, so half of the power is delivered in the output. So this is the way we can explain it. So So far we have studied this construction and VI characteristics, what is the utility of all these. So as far as its utility is concerned, it is the very frequently used for the triggering of the track devices. So sometimes DIAC is used along with the track in a single unit, we call that quad DIAC. And there is hardly any use of DIAC where it is put into use in the circuit independently. So that is why a single pack comes in the markets. We call that quad DIAC. Track definitely needs a triggering device, and DIAC is best suited for that. That is why the quad DIAC is available in the market. And all the application, wherever the track is put into use in the circuit, obviously DIAC will be there. So as far as application is concerned, wherever the track is there, DIAC will be there. Okay? DIAC is never used in the standalone mode in any circuits. So when the DIAC is used with the AC or DC, it works as a Shockley diode. We already have studied that in previous videos. And when it is used in AC, it is working as a DIAC itself. So this was all about of the diode or DIAC. Till then, bye bye.